Hello everyone. So in this video, we'll continue with the intuitive analysis of voltage gain calculation for this common source amplifier without consideration of, I can say, small signal model. So last video, okay, this was previous. In this last video, I calculated the voltage gain for common source amplifier with NMOS. So my target was to first compute these three voltages. My target was to compute these three voltages. This these three voltages: VGS, VDS, and VBS. And this equation, we know that ID is equal to GM VGS and V out equal to minus ID. And with that, we'll calculate this gain. And same for the PMOS, we also calculated these three voltages. And after that, these two equations, and we got the voltage gain. In this video, if I'm considering the channel length modulation parameter and body effect, then again we have to calculate these three voltages only. So, okay. So now, if I'm considering these parameters also, so look at this structure. Actually, in this structure, you cannot see that where this lambda is available, or can say uh, where this body effect is available. But yes, if body is given to connected with some, because body is always considered the lower potential, that is a zero. It is assumed that body is connected as zero. So here you can see that source is also zero, so no body effect is there. But if let's suppose this source is not at zero, suppose the source is not at zero, this is at Vs potential. Okay. If this source is at Vs potential, it may be that some structure R may be connected here, but right now no R is there. So this Vs is just assume that Vs is there because I want to show the body effect here. So for now, this R is not there. R is not there. Just I taken. In later videos, I will show this effect of this resistor. So for this, if I write these three equations, first consider this as zero. And if I write the three equations, okay, so three equations of voltage. So first is your VGS, second is your VDS, and third is your VBS. So in all the three cases, we know that your source is at also the potential. So it is nothing but a VG minus VS, that is your VG minus VS, V in minus your VS. And this drain is nothing but connected to the V out. So it is V out minus VS. And third, your body is connected to zero or ground, and your source is some potential VS. So it is minus VS. So from this thing, you can see that source voltage is available in all three equations of this voltages. So for that, uh, okay, we calculated these three voltages. Now we have to write the equation of current. So the current equation for, if I'm considering all three voltages, then this is nothing but GM VGS. You should know this. GM VGS plus GMB plus GMB BBS plus now. Now let the focus. Okay. So third is VDS by R. So these three terms are going to contribute inside your current ID. And this is the first equation. And second equation is same. That is your current minus ID is flowing across this ID. So RD. So this is going to give you the V out. V out is equal to minus ID RD. So this is the second equation. So if I put all the values of VGS, BBS, and VDS inside the first equation, we'll get the value of ID in terms of V in, V out, and VS. So from this first equation, okay, from this first equation, we will get the value of ID as the function of input voltage, output voltage, and source voltage. So these V in, V out, and Vs are available in ID. So now the point is we have two equations. One is a V out relating the ID, and the second is your ID is a function of V in, V out, and Vs. So with these two equations, if this Vs is also variable, then we cannot compute the gain here. So this Vs should be nothing but a function of, so this Vs should be nothing but a function of either your V in or your V out or your ID. So this thing we have to be careful. So you have to understand this thing. You have to understand this thing very carefully. What I mean to say, this ID is nothing but a volt current that consists of three terms. That is VGS, which is nothing but V in minus Vs. Second is your VBS. So first was VGS. Second is BVS. It is consist of V out minus Vs. And third term consisting VDS. Okay, sorry. So this is consisting V out minus Vs, and second term is BVS, which is minus Vs. So overall, this ID is nothing but a function of input voltage, output voltage, and this S, Vs. So we have only two equations, one relating the ID with the V out, and second ID with these all voltages, input, output, and Vs. So this Vs voltage should be the function of V in, V out, either V in, V out, or ID. So if this is a function of any of these three, we can compute the voltage gain from here. Because if ID is calculated, then put that ID inside this equation, second equation. So we'll get the V out is equal to just minus ID, whatever we calculated or computed from here, and through ID, RD. So for now, I can say if this your VS is nothing but some K times of ID, let's suppose this VS is nothing but a K time of ID. So now put the value of this Vs inside, or can say not inside. So yeah, put your Vs in, yeah, ID. So what will get the ID? So yeah, ID is, so I'm coming here. So ID is nothing but GM. VGS is what? GM. VGS is your V in minus KID. And the second term is this is GM. Second term is GMB. VBS means minus KID. And the third term is nothing but VDS. So what is VDS? VDS is V out minus VS divided by R out. Okay. So I should write here this again. Okay. So I should write here. Uh, okay. So I should write here VS. So this VS is nothing but, okay. This VS is again KID. So from this equation, you can separate the ID term on one side. So ID is can say 1 plus GMK plus GMBK plus KYR. So this ID is separated on one side, and on the other side we have GM yeah, GMV in plus V out by R naught. This will be your third equation after putting all the values of. So this will be the third equation. And in third equation, we can put ID is equal to minus V out by RD. So this thing is coming from second equation. So this is your fourth equation, can say, or nothing but a modification of this second equation. So now put this ID in this third equation, we'll get the relation between V out and V in. So we'll get the relation between V out and V in. So you'll get this voltage gain here. So I think you are clear with this concept. Here I considered this thing is important. Here I considered this Vs is a function of ID. So this Vs can be the function of, yeah, I've considered this Vs as a function of ID. So is a KID. This Vs can also be in some structures. This Vs can also be the function of your, suppose K1 of V in, or it can also be the function of your V out. Whatever it is, if you put this value of Vs inside the equation or the first equation, or can say inside this Vs, Vds, and V in values, you will get the exact relation between ID and V in V out. And second relation is this ID versus V out. So you'll get the relation between V out and V in. This is the voltage gain. So now if I elaborate this thing for the PMOS, next video, not the next video, not next slide. So if I elaborate this thing for PMOS, there's a DC voltage, and this is an input, small signal voltage. And here we are taking the output across the ID. So again, I can say that this is a 0 for DC and AC analysis, and consider this model. So in this model, the first equation, simply write the first equation easily. That is your V out equal to ID cross RD. So here I'm writing this equation because we know that ID is flowing across this RD. Now, again, write these three values of voltages. That is your VSG, and the second your VSB. So this body is connected to source, or if this body is not connected to source, or it's simply connected to VDD, VG is your V in, so it will be like this, and this VS is nothing but, sorry, I should say here minus. Okay, third thing is your VS minus VD. So yeah, this thing is going to give you nothing but VS minus V out. This drain is connected to output voltage. So again, write the equation of for this drain current. Drain current is nothing but equal to GM VSG plus GMB VSB plus VSD by R. So this is the second equation. In second equation, this source voltage has to be the function of something. Again, I can say source voltage has to be the function of either current or V in or V out. Okay. So this, let's suppose this Vs is nothing but a function of your current, and can say KID. Then again, put this value in equation second, and you'll get the function ID is nothing but GM. VSG is no now. Yeah. So this is small KID minus V in, and GMB, and it is your KID. So actually, it will not be KID. It will be minus KID, because we can see here the current is coming here, and this, yeah. If I'm considering there, let me clear this thing. So if this is your source, and let some element is connected here, and the current is going to this side, ID, or can say IS, and this is grounded. Let me clear this thing. So if this element, suppose this any element is R is connected here, let this thing I'll clear later on what the effect of this R. But for now, if I compute this voltage of the source, then what is the Vs? Vs is nothing but minus R times of ID. So I can say I should take this Vs as a minus KID, not plus KID, because it will give some error in calculation. So it will be minus KID. So here will be minus KID, or here minus KID, and minus or VB. That is your 0, because it was connected with the VDD. Okay. So for this diagram, when your body is shorted with source, you'll get VB 0. But so for I need some modification. Okay, I need some modification. Yes, in this diagram, body effect will not come into the picture. So for that, I need to consider this. This your, you can say, connected to VDD. So yeah. So for the PMOS, we need to consider this body voltage to the highest potential, that is a VDD, and this source is separate, that is connected to the resistor, then a VDD. So we'll get like this, Vs equal to this. So because this Vs is VDD is 0, so for the AC analysis, your body is at 0 potential. That's why I put the 0 here. That's why I put the 0 here. Now third term is okay. Now the third term is what you know, VST. Yeah. So third term is VST, which is nothing but your uh, yeah, VS source is again minus K ID and minus V out divided by R naught. So from here you can separate your ID on one side. You can separate ID on one side. You'll get some constant here, and on the right hand side you'll get the minus GMV in and minus V out by R out. So from this third equation, we have ID as a function of V in and V out. And from the first equation, this ID is nothing but from the first equation, this ID is V out by ID. So put this value of ID in the third equation. So we can get here this third equation will result into the only V out and V in. So from here we can calculate this ratio. Okay. So this is your answer of voltage gain. So I think I was able to clear this thing. How to consider the channel length modulation parameter and body effect in both PMOS and NMOS without drawing the small signal model, you can calculate the gain. So the major things to be focused here is you have to be consider this Vs as a function of either current, voltage output or voltage input. You cannot calculate it without consideration that, or and it will come when we will deal with the questions. Then this source voltage in both the cases will come as a function of current voltage or input voltage also. So I think this is enough for this video, and uh, thank you.